Gravity, the invisible force that keeps our feet planted firmly on the ground, the same force that guides planets around stars and stars around galactic centers. From the smallest particles to the largest structures in the cosmos, gravity shapes our universe in profound ways. Yet for all its familiarity, gravity remains deeply mysterious. And perhaps no question about gravity is more intriguing than this. How fast does it travel? When the sun rises each morning, we see its light after it has journeyed across 93 million miles of space, taking about 8 minutes and 20 seconds to reach our eyes. But what about the sun's gravitational pull? Does it reach us instantaneously? Or does it too have a speed limit? This question has fascinated scientists for centuries, leading to some of the most beautiful and revolutionary theories in physics. Tonight, as you rest and listen, we'll explore this cosmic mystery together, traveling through the history of human understanding and into the frontiers of modern science. Imagine if our sun suddenly disappeared. Would Earth continue orbiting the vacant space before drifting away? Or would we feel the change immediately? The answer lies in understanding the speed at which gravity propagates through the fabric of space-time. Throughout human history, our understanding of gravity has evolved dramatically. Ancient cultures recognized gravity's effects, but couldn't explain them. The Greek philosopher Aristotle believed heavy objects naturally sought the center of the Earth, while lighter ones like fire and air moved upward to their natural places. For nearly 2,000 years, this view prevailed. Then came the scientific revolution of the 16th and 17th centuries. Galileo Galilei demonstrated that objects of different weights fall at the same rate when air resistance is negligible. But it was Isaac Newton who gave us the first mathematical description of gravity in 1687. Newton's law of universal gravitation described how every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. This elegant formula explained everything from falling apples to the orbits of planets with astonishing accuracy. But there was something curious about Newton's theory. It seemed to imply that gravitational effects propagated instantaneously across any distance. If the sun moved, Earth would immediately feel the change in gravitational pull, no matter how far away. This suggested that gravitational information could travel at infinite speed, faster than light itself. For more than 200 years, this apparent instantaneous action at a distance troubled physicists. It seemed to violate a basic principle that would later emerge from Einstein's theories, that nothing, not even information, can travel faster than light. The dawn of the 20th century brought a revolution in our understanding of gravity. In 1915, Albert Einstein published his general theory of relativity, completely reconceiving gravity not as a force pulling objects toward each other, but as the curvature of space-time itself. According to Einstein, massive objects like the sun create a depression in the fabric of space-time, similar to how a bowling ball would deform a stretched rubber sheet. Smaller objects like Earth then move along the curves and dips in this fabric. What we experience as gravity is actually the geometry of space-time guiding our motion. This beautiful theory made a specific prediction about gravity's speed. Einstein's equations showed that changes in gravitational fields should propagate as waves traveling at exactly the speed of light, no faster and no slower. But how could we test this prediction? Gravity is the weakest of the four fundamental forces, and gravitational waves would be incredibly subtle, causing distortions in space-time smaller than the width of a proton. Measuring such tiny effects seemed impossible. For decades, the speed of gravity remained a theoretical question without experimental verification. Some physicists continued to wonder if gravity might be special, perhaps the one phenomenon that could transmit information faster than light, potentially opening doors to exotic physics like time travel or communication with the past. Others pointed out that if gravity propagated instantaneously, it would violate Einstein's principle of relativity, potentially creating logical paradoxes where effects could precede their causes in some reference frames. The stakes were high. The speed of gravity wasn't just an academic curiosity, but a fundamental question about the nature of our universe and the limits of causality itself. As you drift towards sleep, imagine these invisible gravitational waves rippling through the space-time around you right now. From distant black holes, merging billions of light years away, to the gentle tug of our moon causing ocean tides, gravity connects all matter across the cosmos. In the coming chapters, we'll explore how scientists finally measured gravity's speed, the remarkable detectors that captured gravitational waves for the first time in human history, and what these discoveries tell us about the fundamental nature of reality. We'll ponder whether theoretical possibilities might still allow gravity to exceed light speed in certain exotic scenarios, and what quantum gravity theories suggest about the true nature of gravitational force carriers. But for now, feel the gentle pull of Earth's gravity holding you safely in place, and consider that this comforting sensation travels to you at precisely the same speed as the starlight twinkling outside your window. The mystery of gravity's speed connects us to the deepest questions in physics, from the nature of space-time to the unification of quantum mechanics and relativity. It's a testament to human curiosity that we continue to probe these profound questions, expanding our understanding of the cosmic dance that governs everything from falling raindrops to colliding galaxies. So relax and allow your mind to drift with these gravitational currents as we begin our journey through one of the most fascinating questions in modern physics. Is the speed of gravity actually faster than light? Our journey to understand gravity's speed begins thousands of years ago, when ancient civilizations first pondered why objects fall toward Earth. The Greeks believed heavy objects sought their natural place at the center of the cosmos. Aristotle taught that heavier objects fall faster than lighter ones, an intuitive but incorrect idea that would persist for nearly 2,000 years. It wasn't until the 16th century that our modern understanding of gravity began to take shape. Galileo Galilei conducted his famous experiments, supposedly dropping objects from the Leaning Tower of Pisa, demonstrating that objects of different weights fall at the same rate when air resistance is negligible. This observation challenged Aristotelian physics and laid the groundwork for a mathematical theory of gravity. Then came Isaac Newton. As legend tells, while sitting in his garden in 1666, he watched an apple fall and had a profound insight. Perhaps the same force pulling the apple downward also kept the moon in its orbit around Earth. This connection between terrestrial and celestial phenomena revolutionized our understanding of the cosmos. In 1687, Newton published his universal law of gravitation in his masterwork, Philosophia Naturalis Principia Mathematica. His elegant formula described how every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. This single equation explained everything from falling objects to planetary orbits with remarkable accuracy. But there was something peculiar about Newton's theory. It described gravity as a force acting instantaneously across any distance. If the sun moved, Earth would feel the change in gravitational pull immediately, with no delay whatsoever. This concept of instantaneous action at a distance troubled Newton himself, who wrote that gravity should be innate, inherent, and essential to matter, so that one body may act upon another at a distance through a vacuum, without the mediation of anything else, by and through which their action and force may be conveyed from one to another, is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. Despite his own misgivings, Newton's mathematics worked with extraordinary precision. For over 2 centuries, his theory successfully predicted the motions of planets, moons, and comets, correctly accounting for the tides, and even leading to the discovery of Neptune based on its gravitational effects on Uranus. The notion that gravitational effects propagated instantaneously became accepted scientific doctrine, even as it created philosophical discomfort about apparent faster-than-light information transfer. During the 19th century, a parallel revolution occurred in our understanding of electromagnetism. Scientists like Michael Faraday, André-Marie Ampère, and James Clerk Maxwell discovered that electric and magnetic phenomena are interconnected. Maxwell unified electricity and magnetism into a single theory, showing that electromagnetic waves travel at a specific speed, precisely the speed of light, approximately 300,000 kilometers per second. This remarkable coincidence raised an intriguing question. If electromagnetic effects propagate at a finite speed, why should gravity be instantaneous? The French mathematician Henri Poincaré suggested in 1905 that gravity probably propagates at the speed of light, not instantaneously. He reasoned that a theory of gravity should be consistent with the emerging principle of relativity, which prohibited faster than light transmission of information. Meanwhile, astronomers had noticed something curious about Mercury's orbit. The point of Mercury's closest approach to the Sun, called the perihelion, gradually shifts over time. While most of this precession could be explained by the gravitational influences of other planets, a small discrepancy remained that Newton's theory couldn't account for. This tiny anomaly, just 43 arc-seconds per century, would turn out to be crucial evidence for a new theory of gravity. Enter Albert Einstein. In 1905, he published his special theory of relativity, establishing the speed of light as a universal cosmic speed limit. Nothing could travel faster than light, not even information. This directly challenged Newton's instantaneous gravity. How could Earth know to adjust its orbit immediately if the Sun moved without violating this cosmic speed limit? Einstein spent the next decade wrestling with this problem, developing a completely new theory of gravity that would be compatible with special relativity. The task was enormously difficult, requiring Einstein to master complex mathematics and develop entirely new conceptual frameworks. In November 1915, Einstein presented his general theory of relativity to the Prussian Academy of Sciences, forever changing our understanding of gravity. Rather than describing gravity as a force acting across space, Einstein reconceived it as the curvature of space-time itself. Imagine space-time as a flexible four-dimensional fabric. Massive objects like stars create depressions in this fabric, similar to how a bowling ball would create a dip on a stretched rubber sheet. Other objects then move along these curves, which we experience as gravitational attraction. When a massive object moves, it creates ripples in the fabric of space-time, gravitational waves that propagate outward at exactly the speed of light. Einstein's equations made a clear prediction. Gravity travels at precisely the speed of light, no faster and no slower. His theory also perfectly explained Mercury's anomalous orbit, providing strong evidence that general relativity more accurately described gravity than Newton's theory had. But directly measuring the speed of gravitational effects remained elusive. Unlike light, which we can easily see and measure, gravitational effects are subtle and difficult to isolate from other influences. For most of the 20th century, scientists had only indirect evidence supporting Einstein's prediction that gravity travels at light speed. The first attempt to detect gravitational waves came from physicist Joseph Weber in the 1960s. He built large aluminum cylinders that he hoped would vibrate slightly when gravitational waves passed through them. Weber claimed successful detections, but other scientists couldn't replicate his results, and it was later determined that his equipment wasn't sensitive enough to detect the incredibly weak gravitational waves reaching Earth. A breakthrough came in 1974 when astronomers Russell Hulse and Joseph Taylor discovered a binary pulsar system, two neutron stars orbiting each other. One of these stars was a pulsar, emitting regular radio pulses like a cosmic lighthouse. By carefully timing these pulses over years, Hulse and Taylor observed that the stars were spiraling toward each other at exactly the rate predicted by general relativity if the system were losing energy by emitting gravitational waves. This provided strong indirect evidence that gravitational waves exist and behave as Einstein predicted, earning Hulse and Taylor the 1993 Nobel Prize in Physics. Yet direct detection of gravitational waves, which would allow scientists to measure their speed, remained beyond technological reach. Einstein himself had doubts whether gravitational waves would ever be detected. given their extreme weakness by the time they reach Earth. As the 20th century drew to a close, a new generation of scientists began designing incredibly sensitive instruments, specifically to detect gravitational waves. The Laser Interferometer. Gravitational Wave Observatory, or LIGO, began construction in the 1990s, promising unprecedented sensitivity that might finally allow direct detection of these elusive space-time ripples. The stage was set for one of the most remarkable confirmations of Einstein's theory, one that would finally answer the centuries-old question: exactly how fast does gravity travel through our universe? Imagine dropping a pebble into a still pond. You watch as ripples spread outward in concentric circles, carrying energy across the water's surface. Now imagine something similar happening to the fabric of space-time itself. This is the essence of gravitational waves, ripples in the very structure of space and time that carry gravitational energy across the cosmos. Einstein's general theory of relativity predicted these waves in 1915. Just as accelerating electric charges create electromagnetic waves, accelerating masses create gravitational waves. These waves travel through empty space at precisely the speed of light, carrying information about changes in gravitational fields. But what exactly are these waves? To understand them, we need to grasp how Einstein reconceived gravity. In general relativity, space-time isn't a fixed, rigid stage where cosmic events unfold. Instead, it's a dynamic, flexible, four-dimensional fabric that can stretch, compress, and curve in response to matter and energy. Massive objects, like stars and planets, create curves in this fabric. When these masses move, especially when they accelerate, they create disturbances in space-time that propagate outward as waves. These gravitational waves alternately stretch and compress space-time as they pass through. Like sound waves alternately compress and rarefy air. The effects of these waves are incredibly subtle. By the time gravitational waves from cosmic events reach Earth, they typically change distances by less than the width of a proton. Detecting them requires instruments of extraordinary sensitivity, capable of measuring changes in length of about 1 part in 10 to the power of 21. That's like measuring the distance to the nearest star, with an accuracy smaller than the width of a human hair. For most of the 20th century, gravitational waves remained a theoretical prediction, too subtle to detect directly. Some physicists even debated whether they carried real physical energy or were merely mathematical artifacts of Einstein's equations. The debate was settled in 1974 when astronomers Russell Hulse and Joseph Taylor discovered PSRB 1913+16, a binary system consisting of a pulsar orbiting another neutron star. A pulsar is a rapidly rotating neutron star that emits regular pulses of radio waves, acting like a precise cosmic clock. By carefully timing these radio pulses over several years, Hulse and Taylor observed that the orbital period of the binary system was decreasing exactly as general relativity predicted if the system were losing energy by emitting gravitational waves. This indirect evidence convinced most scientists that gravitational waves were real physical phenomena, carrying energy away from accelerating masses. But direct detection remained elusive. The challenge was enormous, detecting changes in length thousands of times smaller than the nucleus of an atom. Various detection methods were proposed and attempted. The first serious efforts came from physicist Joseph Weber in the 1960s. He built large aluminum cylinders, reasoning that passing gravitational waves would cause these Weber bars to vibrate at specific resonant frequencies. Weber claimed successful detections, but other scientists couldn't replicate his results. We now know his detectors weren't sensitive enough to detect the gravitational waves reaching Earth. In the 1980s, scientists began developing a more sensitive detection method using laser interferometry. The basic concept is ingenious. Split a laser beam and send the two resulting beams down perpendicular arms. Reflect these beams back with mirrors and recombine them. If both arms remain exactly the same length, the recombined light forms a stable pattern. But if a gravitational wave passes through, stretching one arm while compressing the other, the pattern changes. By measuring these changes, scientists can detect gravitational waves. This concept led to the construction of the Laser Interferometer Gravitational Wave Observatory, known as LIGO. With facilities in Hanford, Washington, and Livingston, Louisiana, LIGO consists of L-shaped detectors with arms 4 kilometers long. The dual locations allow scientists to confirm that signals detected aren't just local vibrations or noise. After an initial run from 2002 to 2010 without detecting gravitational waves, LIGO underwent a major upgrade. The Advanced LIGO project improved the detector's sensitivity by a factor of 10, making them capable of detecting gravitational waves from sources up to 10 times farther away. This expanded the observable volume of space by a factor of 1,000. On September 14, 2015, both LIGO detectors registered a signal that matched the predicted pattern of gravitational waves. The signal, designated GW150914, lasted for about 0.2 of a second and increased in frequency from 35 to 250 Hz before disappearing. Scientists determined that this signal came from the final moments of two black holes merging. Located about 1.3 billion light-years away, these black holes had masses of about 29 and 36 times the mass of our Sun. As they spiraled toward each other, they accelerated to nearly half the speed of light before colliding and forming a single black hole. In the process, about 3 solar masses were converted directly into gravitational wave energy, briefly outshining all the stars in the observable universe combined, though only in gravitational waves, not in light. This detection was a triumph of both theory and engineering. It confirmed a century-old prediction of Einstein's general relativity and demonstrated humanity's ability to build instruments of almost unimaginable precision. The 2017 Nobel Prize in Physics was awarded to Rainer Weiss, Barry Barish, and Kip Thorne for their decisive contributions to the LIGO detector and the observation of gravitational waves. Since that first detection, the LIGO scientific collaboration, together with the European Virgo detector, has observed dozens more gravitational wave events. Most come from merging black holes, but some originate from neutron star collisions, which also produce light and other electromagnetic radiation. These multi-messenger observations have opened an entirely new way to study the universe. The detection of gravitational waves allows us to observe phenomena invisible to traditional telescopes. Black hole mergers emit no light, making them invisible to conventional astronomy. But through gravitational waves, we can now hear these cosmic collisions. Scientists often describe gravitational wave astronomy as adding sound to our cosmic senses, complementing the light-based astronomy we've practiced for centuries. Gravitational waves also provide a way to test Einstein's prediction that they travel at exactly the speed of light. But how can we measure the speed of these waves? The waves themselves carry no identifying information about when they were created. To measure their speed, scientists need an independent way to determine when the wave-generating event occurred. The breakthrough came on August 17, 2017, when LIGO and Virgo detected gravitational waves from a neutron star merger, designated GW170817. Unlike black holes, colliding neutron stars produce electromagnetic radiation, including gamma rays, visible light, radio waves, and X-rays. Just 1.7 seconds after the gravitational wave signal, NASA's Fermi Gamma Ray Space Telescope detected a gamma ray burst from the same region of sky. This near-simultaneous arrival of gravitational waves and light provided the first direct evidence that gravitational waves travel at the speed of light. The tiny 1.7-second difference over a journey of 130 million light-years means the speeds of gravity and light differ by less than 1 part in 10 to the power of 15. This remarkable confirmation vindicated Einstein's century-old prediction and definitively answered our question: Gravity propagates at exactly the light speed, not instantaneously as Newton had assumed, and not faster than light as some alternative theories had proposed. The nature of gravitational waves reveals something profound about our universe. Space-time itself is dynamic, capable of carrying energy and information across vast cosmic distances. The ripples in space-time connect distant events, binding the cosmos together through gravitational influence that travels precisely at the cosmic speed limit. As you rest, consider that gravitational waves from distant cosmic cataclysms are passing through your body right now, gently stretching and compressing the space you occupy by an infinitesimal amount. These subtle messengers connect us to the most energetic events in the universe, a constant reminder that we are part of a dynamic, interconnected cosmic whole. How do you measure the speed of something invisible? This challenge has confronted scientists seeking to determine exactly how fast gravity travels. Unlike light, which we can directly observe, gravity's effects are subtle and often entangled with other forces. Let's explore the ingenious experiments and observations that have finally answered this centuries-old question. Throughout most of human history, gravitational effects were assumed to be instantaneous. When Newton formulated his law of universal gravitation in the 17th century, this assumption went unchallenged. After all, the orbits of planets seem to respond immediately to the gravitational influence of the Sun. The first serious scientific consideration that gravity might have a finite speed came after Maxwell's theory of electromagnetism in the 1860s. Maxwell showed that electromagnetic waves travel at the speed of light. This raised the possibility that gravity, another fundamental force, might also propagate at a finite speed. In Einstein's 1915 general theory of relativity, gravity isn't a force transmitted through space, but a manifestation of space-time curvature. Changes in this curvature would propagate as gravitational waves at exactly the speed of light. But how could scientists test this prediction? One of the earliest indirect tests came from studies of Mercury's orbit. Mercury follows an elliptical path around the Sun, and the point of its closest approach, called the perihelion, gradually shifts over time. Most of this precession could be explained by the gravitational influences of other planets, but a small discrepancy of 43 arcseconds per century remained unexplained by Newton's theory. Einstein's general relativity, accounting for gravity propagating at light speed rather than instantaneously, perfectly predicted this anomalous precession. This success provided strong indirect evidence for Einstein's theory, but didn't directly confirm gravity's speed. More compelling evidence came from timing the radio pulses from binary pulsar systems. Pulsars are rapidly rotating neutron stars that emit regular radio pulses with extraordinary precision, functioning like cosmic clocks. When a pulsar orbits another star, its pulses arrive at Earth slightly earlier or later depending on its position in the orbit. The binary pulsar PSRB 1913+16, discovered by Russell Hulse and Joseph Taylor in 1974, provided an ideal natural laboratory. By timing its pulses over several years, they observed that the orbital period was decreasing at exactly the rate predicted by general relativity if the system were losing energy through gravitational wave emission. This observation earned Hulse and Taylor the 1993 Nobel Prize in Physics and provided strong evidence that gravitational effects propagate at light speed. If gravity were instantaneous, the orbital decay would follow a different pattern. Another indirect test came from observing the deflection of starlight during solar eclipses. Einstein predicted that light passing near the Sun would be bent by the Sun's gravitational field, and that the amount of bending would depend on gravity propagating at light speed. Observations during the 1919 solar eclipse confirmed Einstein's predictions, providing another piece of indirect evidence. But scientists wanted more direct confirmation. They needed to observe both gravitational and electromagnetic signals from the same cosmic event and compare their arrival times. This required detecting gravitational waves, something that wouldn't be possible until the 21st century. The breakthrough came with the development of the Laser Interferometer Gravitational Wave Observatory, or LIGO. After major upgrades to improve sensitivity, advanced LIGO began operating in 2015. On September 14th of that year, both LIGO detectors captured gravitational waves from the merger of two black holes, about 1.3 billion light-years away, designated GW 150914. This historic detection confirmed that gravitational waves exist, but it couldn't directly measure their speed. Since black holes typically don't emit electromagnetic radiation, there was no light signal to compare with the gravitational wave arrival time. The crucial observation came on August 17, 2017. On that day, LIGO and its European counterpart Virgo detected gravitational waves from a different kind of cosmic collision. Two neutron stars merging about 130 million light-years away in a galaxy called NGC 4993. Unlike black holes, neutron star mergers produce spectacular electromagnetic fireworks across many wavelengths. Just 1.7 seconds after the gravitational wave signal reached Earth, NASA's Fermi Gamma Ray Space Telescope detected a short gamma ray burst from the same region of sky. In the following days and weeks, observatories around the world and in space detected X-rays, ultraviolet light, optical light, infrared, and radio waves from this event, designated GW 170817. This multi-messenger observation provided the first direct test of gravity's speed. The gravitational waves and gamma rays had traveled through space for about 130 million years before reaching Earth just 1.7 seconds apart. This tiny difference over such an enormous journey means the speeds of gravity and light differ by less than 1 part in 10 to the power of 15. For all practical purposes, gravity travels at exactly the speed of light, confirming Einstein's century-old prediction. Why was there even a 1.7-second delay between the gravitational waves and gamma rays? Scientists believe this reflects the time it took for the merger to produce the gamma ray burst, not a difference in travel speed. The gravitational waves were emitted during the final moments of the neutron star's spiral towards each other, while the gamma rays were produced after the collision as jets of particles formed and broke through the surrounding material. Further confirmation came from subsequent neutron star mergers detected by LIGO and Virgo. In each case where electromagnetic counterparts were observed, the arrival times were consistent with gravitational waves traveling at light speed. Another ingenious test of gravity's speed comes from observing the timing of binary star systems. If gravity propagated at a speed different from light, the gravitational influence of one star on another would be slightly displaced from its apparent position, causing a characteristic distortion in the orbit. Careful observations of binary star systems show no such distortion, confirming that gravity travels at light speed to high precision. Scientists have also analyzed gravitational lensing, the bending of light from distant galaxies by massive objects closer to us. These observations allow them to map the distribution of mass in the universe and test predictions of general relativity. The results consistently support Einstein's theory, including the prediction that gravity propagates at light speed. Perhaps the most comprehensive test comes from observing the cosmic microwave background radiation, the afterglow of the Big Bang. This radiation carries imprints of primordial gravitational waves, and its pattern is influenced by the speed at which gravity propagates. Analysis of this radiation by missions like WMAP and Planck supports the conclusion that gravity travels at light speed, with constraints ruling out significant deviations. What about the Earth's orbit around the Sun? If the Sun suddenly disappeared, Newton's instantaneous gravity would have Earth immediately fly off in a straight line. In Einstein's theory, we wouldn't know about the Sun's disappearance until 8 minutes later, when both the lack of sunlight and the change in gravitational field reached us at light speed. Our planet would continue in its curved path for those 8 minutes, oblivious to the Sun's absence, before suddenly being released from its gravitational influence. Of course, we can't make the Sun disappear to test this, but our understanding of celestial mechanics based on general relativity, with gravity propagating at light speed, matches observations with extraordinary precision. NASA's planetary navigation, which guides spacecraft throughout our solar system, relies on Einstein's equations and would fail if gravity traveled at a significantly different speed. Laboratory experiments on Earth provide additional confirmation. The Gravity Probe B satellite, launched in 2004, measured how Earth's rotation warps the fabric of space-time around it, an effect called frame dragging. The results match general relativity's predictions within 2%, further validating Einstein's theory. The Microscope satellite mission, which ran from 2016 to 2018, tested the equivalence principle, a cornerstone of general relativity, with unprecedented precision. The equivalence principle states that gravitational mass and inertial mass are identical, which is a key assumption in deriving that gravity travels at light speed. Microscope confirmed the equivalence principle to a precision of 1 part in 10 to the power of 14, providing additional support for general relativity's description of gravity. The accumulated evidence from astronomical observations, gravitational wave detections, laboratory experiments, and mathematical consistency leaves no reasonable doubt. Gravity propagates at exactly the speed of light, no faster and no slower. Einstein's prediction has withstood over a century of increasingly precise tests. This conclusion has profound implications for our understanding of the universe. It means that gravitational information, like all other information, is bound by the cosmic speed limit. There is no instantaneous action at a distance. The influence of gravity, like light, takes time to travel across space, linking cause and effect in a way that preserves the causal structure of space-time. As you rest, imagine the gravitational waves from countless cosmic events washing over you, traveling at precisely the same speed as the starlight twinkling outside your window. Both are messengers from distant parts of our universe, bound by the same fundamental limit that ensures the orderly progression of cause and effect throughout the cosmos. Despite the strong experimental evidence that gravity propagates at exactly the speed of light, the question persists: is it possible that gravity might travel faster than light under certain circumstances? This isn't merely idle speculation. Throughout the history of physics, seemingly settled questions have sometimes yielded surprising new insights when examined more deeply. Let's explore the theoretical possibilities, understanding why faster-than-light gravity would be controversial, and examining whether any loopholes might exist in our current understanding. Einstein's special relativity established the speed of light as a universal cosmic speed limit. According to this theory, nothing with mass can accelerate to the speed of light because it would require infinite energy. Moreover, nothing can transmit information faster than light without violating causality, potentially leading to logical paradoxes where effects precede their causes. General relativity, Einstein's theory of gravity, is built upon this foundation and describes gravity as the curvature of space-time propagating at exactly light speed. The remarkable agreement between general relativity's predictions and experimental observations gives us confidence in this description. But science progresses by questioning established theories and looking for situations where they might break down. Several theoretical approaches have explored whether gravity might exceed the light speed limit. One early challenge came from Laplace in the late 18th century, who calculated that if gravity propagated at a finite speed, planetary orbits would become unstable due to an aberration effect. Since planetary orbits appear stable, he concluded that gravity must propagate much faster than light, effectively instantaneously. However, Laplace didn't account for the relativistic effects described in Einstein's theories. When these are properly included, the aberration effect is exactly cancelled by velocity-dependent terms in the gravitational field, preserving stable orbits even with gravity propagating at light speed. Another approach considers whether the hypothetical particles that would carry the gravitational force, called gravitons, might have properties that allow them to exceed the light speed barrier. In quantum field theory, particles like photons that travel at light speed must be massless, Conversely, particles with mass, like electrons, must travel slower than light. If gravitons have a small but non-zero mass, they would typically travel slower than light. However, some speculative theories suggest gravitons might have exotic properties that allow them to exceed light speed under certain conditions. These theories often involve modifications to Einstein's relativity at very small scales or in extreme gravitational environments. One such possibility comes from theories with extra dimensions beyond the 3 spatial dimensions and 1 time dimension we normally experience. String theory and certain other approaches to quantum gravity propose that our universe might have additional spatial dimensions that are too small or otherwise hidden from our direct observation. In some of these theories, gravitons might take shortcuts through these extra dimensions, appearing to travel faster than light from our 4-dimensional perspective. Imagine ants walking on the surface of a piece of paper. To them, the shortest path between 2 points is along the paper's surface. But if the paper is folded, a 3-dimensional being could move directly through the fold, appearing to the ants to have traveled faster than should be possible. Similarly, if space-time has higher dimensional folds, gravitons might take shortcuts that make them appear to travel faster than light from our perspective. However, this wouldn't violate relativity because the gravitons would still travel below light speed within the higher dimensional space. Another approach comes from theories of deformed special relativity, which propose modifications to Einstein's theory that might allow certain particles to travel faster than light without causing causality problems. These theories often change the structure of space-time at very high energies, potentially allowing faster than light travel while preserving causality through other mechanisms. Certain quantum gravity theories suggest that space-time might have a granular or discrete structure at extremely small scales, rather than being perfectly continuous. These quantum fluctuations in space-time might allow for variations in the speed of gravity depending on the energy of the gravitons, potentially permitting some higher energy gravitons to travel slightly faster than light. Some alternative theories of gravity, like tensor vector scalar gravity or modified Newtonian dynamics, were developed to explain astronomical observations without invoking dark matter. These theories sometimes predict that gravitational effects could propagate differently than in general relativity, potentially faster than light in some cases. However, the 2017 observation of gravitational waves traveling at light speed has significantly constrained these alternative theories. Another speculative possibility involves what physicists call superluminal phase velocities. The phase velocity of a wave describes how quickly the phase of the wave propagates, which can sometimes exceed the speed of light without violating relativity because it doesn't carry information. Some researchers have suggested that certain components of gravitational waves might have superluminal phase velocities, even while the waves themselves, carrying actual gravitational information, remain bound by the light speed limit. Tachyons, hypothetical particles that would always travel faster than light, have been proposed in some theoretical models. A tachyonic graviton would transmit gravitational effects faster than light by definition. However, most physicists consider tachyons problematic because they would allow for causality violations. Moreover, no experimental evidence supports their existence, and they're generally considered mathematical curiosities, rather than realistic physical possibilities. Some theorists have explored whether quantum entanglement might allow for faster-than-light gravitational effects. Quantum entanglement creates correlations between particles that appear to transmit information instantaneously, regardless of the distance separating them. However, careful analysis shows that entanglement cannot transmit usable information faster than light, preserving consistency with relativity. While gravity might have quantum mechanical aspects that involve entanglement, these wouldn't allow for transmitting gravitational information faster than light. Let's consider what would happen if gravity did travel faster than light. The consequences would be profound and problematic. Faster than light gravity would create the possibility of gravitational influences arriving before their causes, potentially creating causality paradoxes. For instance, a massive object moving quickly might create gravitational effects that influence its own past motion, creating logical contradictions. Such paradoxes would undermine the fundamental principle of causality, the notion that causes precede their effects, which is essential to scientific reasoning and our understanding of reality. While not logically impossible, a universe without causality would be extraordinarily difficult to reconcile with our observations and scientific methods. Additionally, if gravity could travel faster than light, it would suggest a privileged reference frame in the universe, contradicting the principle of relativity that all inertial reference frames are equivalent. This would require a dramatic reimagining of fundamental physics. Despite these theoretical explorations, it's important to emphasize that all experimental evidence to date supports Einstein's prediction that gravity propagates at exactly the speed of light. The 2017 observations of nearly simultaneous gravitational waves and gamma rays from a neutron star merger constrain any difference between the speeds of gravity and light to less than 1 part in 10 to the power of 15. This experimental result severely limits the viability of many alternative theories predicting faster than light gravity. For such theories to remain viable, they must either predict deviations too small to be detected by current experiments or apply only in exotic circumstances not tested by the neutron star merger observation. The scientific consensus strongly favors the conclusion that gravity travels at precisely the speed of light, as predicted by general relativity. While theoretical exploration of alternatives continues as part of the healthy scientific process, extraordinary evidence would be required to overturn this well-established understanding. As you rest, consider that the apparent cosmic speed limit may not be a frustrating constraint, but rather a fundamental principle that ensures the logical coherence of our universe. The fact that gravity travels at light speed, no faster and no slower, may be essential for maintaining the orderly relationship between cause and effect that makes our universe comprehensible. The speed of gravity, precisely matched to the speed of light, suggests a profound unity in how fundamental forces operate. Rather than being separate phenomena, light and gravity both reveal aspects of the same underlying reality, the structure of space-time itself. Their shared speed hints at a deeper connection, perhaps pointing toward the long-sought unification of quantum mechanics and general relativity. In our exploration of whether gravity could travel faster than light, we find ourselves confronting the limits not just of gravity's speed, but of our current understanding of physics. The question takes us to the frontiers of theoretical physics, where general relativity meets quantum mechanics, and where our intuitions about space and time are challenged by both mathematical formalism and experimental evidence. While the weight of evidence indicates that gravity travels at precisely the speed of light, the continuing theoretical exploration of alternatives reflects the essential nature of science, a never-ending journey of questioning, testing, and refining our understanding of the universe. At the heart of modern physics lie two extraordinarily successful frameworks: general relativity, which describes gravity as the curvature of space-time, and quantum mechanics, which governs the behavior of particles at the smallest scales. Despite their individual successes, these theories have resisted unification for nearly a century. In the uncharted territory where these theories meet, the question of gravity's speed takes on new dimensions and subtleties. Quantum gravity, the effort to reconcile these frameworks, represents one of the greatest challenges in theoretical physics. Various approaches have been developed, each with its own perspective on how gravity behaves at the quantum level, and by extension, how fast gravitational effects propagate. Let's begin with the concept of the graviton, the hypothetical particle that would carry the gravitational force in a quantum theory of gravity. Just as photons carry the electromagnetic force, gravitons would transmit gravitational interactions. In the simplest quantum field theory approach, gravitons would be massless particles that travel at exactly the speed of light, consistent with Einstein's general relativity. However, quantum effects might introduce complications. In quantum field theory, virtual particles can briefly violate energy conservation, popping in and out of existence in accordance with Heisenberg's uncertainty principle. These quantum fluctuations could potentially affect how gravitational waves propagate, leading to tiny deviations from the classical prediction that gravity travels at exactly light speed. String theory, one of the leading candidates for quantum gravity, replaces point particles with tiny, vibrating strings. Different vibration patterns correspond to different particles, with gravitons arising from particular vibration modes of closed strings. In most string theory formulations, gravitons remain massless and travel at exactly light speed. However, some string theory scenarios suggest intriguing possibilities. In certain brane-world models, where our universe exists on a four-dimensional brane within a higher dimensional space, gravitons might take shortcuts through extra dimensions. From our perspective, this could make gravity appear to propagate faster than light, though within the full higher dimensional space, gravitons would still respect the cosmic speed limit. String theory also predicts corrections to general relativity that become significant at extremely high energies or in very strong gravitational fields. These corrections might subtly alter the propagation speed of gravitational effects in extreme environments, such as near the Big Bang or inside black holes, while remaining consistent with light speed propagation under normal conditions. Another approach to quantum gravity, loop quantum gravity, suggests that space-time itself has a discrete, granular structure at the smallest scales, rather than being perfectly continuous. This quantized geometry might affect how gravitational waves propagate at these scales. Some versions of loop quantum gravity predict energy-dependent modifications to the dispersion relation for gravitons, potentially allowing higher energy gravitons to travel slightly faster or slower than lower energy ones. This phenomenon, called gravitational dispersion, would be similar to how light waves of different frequencies travel at different speeds through a prism, causing white light to separate into its component colors. If gravitational waves exhibit similar dispersion at quantum scales, it could lead to tiny measurable differences in the arrival times of gravitational waves with different frequencies. Causal set theory, another quantum gravity approach, models space-time as a discrete set of points with well-defined causal relationships. This discreteness could potentially introduce small fluctuations in the speed of gravitational wave propagation, leading to a slight fuzziness in arrival times compared to the sharp predictions of classical general relativity. Asymptotic safety is a scenario in quantum gravity where the strength of gravity's interaction might vary with energy scale in just the right way to make the theory mathematically well-behaved at all energy scales. Some asymptotic safety models predict tiny deviations from light speed propagation of gravity at extremely high energies, potentially detectable through precise measurements of gravitational waves from the early universe. Non-commutative geometry approaches to quantum gravity suggest that at very small scales, the coordinates of spacetime might not commute, meaning the order in which you measure position matters. This property could affect how gravitational waves propagate through quantum spacetime, potentially introducing tiny deviations from exact light speed. Emergent gravity theories propose that gravity isn't a fundamental force, but emerges from more basic quantum mechanical processes, similar to how temperature emerges from the collective motion of particles. In some of these theories, gravitational effects might propagate slightly differently than the clean predictions of general relativity, possibly with tiny deviations from exact light speed. How might we detect such small deviations if they exist? One approach involves looking for energy-dependent arrival times in gravitational waves. If higher energy gravitational waves travel at slightly different speeds than lower energy ones, we might detect this dispersion by precisely timing the arrival of different frequency components from gravitational wave events. Another possibility is to compare the arrival times of gravitational waves and light from extremely distant sources. The tiny deviations predicted by quantum gravity theories would accumulate over vast cosmic distances, potentially becoming detectable for sources billions of light years away. The neutron-star merger GW170817, observed in both gravitational waves and light, place strong constraints on such deviations. But even more distant sources might reveal subtle effects. Cosmic microwave background radiation, the afterglow of the Big Bang, contains imprints of primordial gravitational waves from the earliest moments of the universe. Precise measurements of this radiation by future experiments might reveal quantum gravity effects on the propagation of these ancient gravitational waves. Pulsar timing arrays, which monitor radio pulses from multiple rapidly rotating neutron stars, can detect low-frequency gravitational waves passing through our galaxy. These arrays might eventually achieve the precision needed to detect quantum gravity modifications to gravitational wave propagation. Laboratory experiments, though challenging, might eventually probe quantum gravity effects on gravity's speed. Proposed tabletop experiments using quantum systems in superposition could potentially detect tiny deviations from classical gravitational behavior, indirectly testing predictions about gravity's propagation speed. It's important to emphasize that any deviations from light speed propagation of gravity predicted by quantum gravity theories would be extremely small, likely parts per billion or less under normal conditions. These deviations would become significant only at energy scales approaching the Planck scale, about 10 to the power of 19 billion electron volts, far beyond what we can directly probe with current technology. Despite these challenges, the question of gravity's speed at quantum scales remains a crucial test for any viable quantum gravity theory. Any theory predicting significant deviations from light speed propagation under normal conditions would face severe experimental constraints from the 2017 neutron star merger observation, which found that gravity travels at light speed to within 1 part in 10 to the power of 15. The relationship between quantum mechanics and gravity raises other intriguing questions about gravity's speed. In quantum mechanics, the act of measurement plays a crucial role, seemingly causing instantaneous changes across entangled systems. Does this quantum non-locality interact with gravitational effects in any way that might affect how quickly gravitational information propagates? Some theoretical proposals suggest that gravity might play a role in quantum wave function collapse, the process by which quantum superpositions resolve into definite states upon measurement. If true, this connection between gravity and quantum measurement might have subtle implications for how quickly gravitational effects propagate in quantum contexts. Another fascinating quantum consideration involves the Unruh effect, where an accelerating observer perceives the vacuum of space as filled with thermal radiation. This effect, closely related to Hawking radiation from black holes, suggests that our perception of space-time depends on our state of motion. Might this observer dependence affect how different observers perceive the speed of gravitational effects? The holographic principle, inspired by black hole thermodynamics and developed within string theory, suggests that all the information contained in a volume of space can be represented on its boundary. This principle has led to the ADAS-CFT correspondence, a conjectured relationship between gravity in certain spacetimes and quantum field theories without gravity. In this correspondence, gravitational dynamics in the bulk translate to particle interactions on the boundary, potentially providing a new perspective on the propagation speed of gravitational effects. Quantum gravity approaches also raise the possibility that space-time itself might emerge from more fundamental quantum entities, rather than being a primitive concept. If space-time is emergent, then questions about the speed of gravity take on new meaning, as they concern how quickly changes propagate through the collective behavior of the underlying quantum reality. The experimental challenges in probing these quantum aspects of gravity's speed are enormous. The quantum nature of gravity would become directly apparent only at energy scales, or in gravitational regimes far beyond our current experimental reach. Nevertheless, ingenious experiments continue to push the boundaries, seeking indirect evidence of quantum gravity effects. For now, all available evidence supports the conclusion that gravity propagates at exactly the speed of light, as predicted by general relativity. Any deviations, if they exist, must be extremely small and manifest only in exotic regimes. Still, the theoretical exploration of how quantum effects might influence gravity's speed represents an important frontier in our quest to unify physics and understand the fundamental nature of reality. As you drift towards sleep, imagine the quantum fabric of space-time, with gravitons carrying ripples through its structure at light speed. Picture the vast cosmos above you, where neutron stars and black holes send gravitational waves across billions of light years, their journey time providing crucial evidence about the fundamental nature of gravity. The question of gravity's speed at quantum scales reminds us that our understanding of the universe remains incomplete. Far from being discouraging, this incompleteness invites wonder and fuels the continuing scientific journey. The mysteries at the intersection of quantum mechanics and gravity may contain the seeds of the next great revolution in physics, just as the puzzles facing physicists a century ago led to the quantum and relativistic frameworks that transformed our understanding of reality. In the quiet darkness, allow your thoughts to gently explore these cosmic mysteries, not with urgency, but with peaceful curiosity. The universe has taken billions of years to evolve to this moment, and the greatest questions in physics will unfold in their own time. For now, rest in the knowledge that gravity's gentle pull, traveling at the speed of light across the cosmos, holds you safely on Earth as you journey through the night. The speed at which gravity propagates shapes our universe on the grandest scales. From the expansion of space to the formation of galaxies and the mysterious phenomena of dark energy and dark matter, gravity's finite speed plays a crucial role in cosmic evolution. Let's explore how the fact that gravity travels at light speed, no faster and no slower, influences our understanding of the cosmos as a whole. The story of our universe begins with the Big Bang, an extraordinarily hot and dense state from which space itself has been expanding for approximately 13.8 billion years. In the earliest moments of this expansion, the universe underwent a brief but crucial period of accelerated expansion called cosmic inflation. During inflation, space expanded exponentially, stretching tiny quantum fluctuations into the seeds of cosmic structure. The finite speed of gravity played a vital role in this process. Because gravitational effects cannot propagate faster than light, regions of space that expanded away from each other faster than light became causally disconnected, meaning they could no longer influence each other gravitationally or in any other way. This limitation created what cosmologists call particle horizons, boundaries beyond which we cannot receive signals from the early universe. The observable universe, everything we can potentially see, is limited by these horizons. If gravity propagated instantaneously, as in Newton's theory, these horizons wouldn't exist, and the structure of the cosmos would be radically different. After inflation, the universe continued expanding, though at a slower rate. Matter gradually clumped together under gravity's influence, forming the first stars and galaxies. This process of structure formation depends critically on how quickly gravitational effects propagate. Computer simulations of cosmic evolution must account for gravity traveling at light speed to accurately model how structure forms. If gravity were instantaneous, matter would clump together much more efficiently, likely resulting in a universe with fewer, larger structures, rather than the intricate cosmic web we observe. The finite speed of gravity also affects the stability of large structures like galaxy clusters. These massive collections of galaxies are held together by gravity, but would fly apart without the invisible scaffolding of dark matter. The precise distribution of dark matter in these clusters depends on gravitational effects propagating at light speed. One of the most profound cosmological implications of gravity's speed involves the accelerating expansion of the universe. In 1998, astronomers discovered that the expansion of space is speeding up, contrary to the expectation that gravity should be slowing it down. This acceleration is attributed to dark energy, a mysterious form of energy that permeates all of space and acts repulsively. The nature of dark energy remains one of the biggest puzzles in cosmology. Some theories suggest it might involve modifications to how gravity works on the largest scales. These modified gravity theories must carefully account for the speed at which gravitational effects propagate to remain consistent with observations showing that gravity travels at light speed. The standard model of cosmology, called lambda CDM, lambda cold dark matter, incorporates Einstein's general relativity with gravity propagating at light speed. This model successfully explains a wide range of observations, from the cosmic microwave background radiation to the large-scale distribution of galaxies. Any viable alternative must match these successes while respecting the experimental constraints on gravity's speed. Let's explore a fascinating thought experiment. What if gravity propagated much faster than light, or even instantaneously? How would our cosmos differ? In such a universe, the evolution of cosmic structure would be dramatically altered. Gravitational effects would reach across vast distances immediately, allowing matter to respond instantly to the gravitational pull of distant masses. This would likely result in more efficient structure formation, with matter clumping together more rapidly than in our universe. The accelerating expansion of the universe might also be affected. In some modified gravity theories that attempt to explain dark energy, the propagation speed of gravitational effects plays a crucial role. If gravity traveled faster than light, these theories would predict different expansion histories than what we observe. The cosmic microwave background radiation, the afterglow of the Big Bang, would also appear different. This radiation shows tiny temperature fluctuations that reflect the distribution of matter in the early universe. The pattern of these fluctuations depends on how quickly gravitational effects could propagate. So a universe with faster than light gravity would likely show different patterns than what our telescopes detect. Even the phenomenon of gravitational lensing, where the light from distant galaxies is bent by the gravity of intervening mass, would be altered. The bending of light depends on the interplay between electromagnetic waves and gravitational effects, both propagating at the same speed. If gravity traveled faster, the observed patterns of lensing would differ from what we see. Another important cosmological implication involves what physicists call gravitational memory. This is a permanent displacement in space-time caused by passing gravitational waves. Because gravitational waves travel at light speed, this memory effect propagates at the same pace, affecting how space-time itself carries the imprint of past cosmic events. The discovery of gravitational waves has opened a new window on the cosmos, allowing us to detect events that emit little or no electromagnetic radiation, such as black hole mergers. The fact that these waves travel at light speed means the information they carry about distant cosmic cataclysms takes precisely the same time to reach us as light would, had it been emitted from the same events. This equivalence becomes crucial when studying multi-messenger astronomy, where both gravitational waves and electromagnetic signals are detected from the same source. The near-simultaneous arrival of gravitational waves and gamma rays from the neutron star Merger GW 170817 not only confirmed gravity's speed, but also allowed astronomers to pinpoint the source galaxy and study it with conventional telescopes. The finite speed of gravity also affects our interpretation of redshift, the stretching of light waves from distant galaxies due to cosmic expansion. The patterns of galaxy clustering we observe depend on both the distribution of matter and how quickly gravitational effects propagate through the cosmos. Our models of large-scale structure rely on gravity traveling at light speed to correctly interpret these patterns. Perhaps one of the most profound implications concerns the horizon problem in cosmology. The cosmic microwave background radiation appears remarkably uniform in temperature across the entire sky, suggesting that the early universe reached thermal equilibrium. But if distant regions of the observable universe were never in causal contact, because nothing, including gravity, can travel faster than light, how did they reach the same temperature? Cosmic inflation provides a solution to this puzzle. Before inflation, the regions that now appear disconnected were actually close enough to interact and reach thermal equilibrium. Inflation then rapidly expanded space, pushing these regions beyond each other's gravitational influence. This solution depends critically on the fact that gravity propagates at a finite speed, specifically the speed of light. Dark matter, the invisible substance that appears to make up about 85% of the matter in the universe, also interacts with normal matter primarily through gravity. The distribution of dark matter in galactic halos and across the cosmic web is shaped by gravitational effects propagating at light speed. Computer simulations of dark matter distribution must account for this finite propagation speed to match observations. The future fate of the universe likewise depends on how gravity operates across cosmic distances. Current observations suggest that dark energy will cause the expansion to continue accelerating indefinitely, eventually pushing galaxies beyond our observable horizon. This scenario assumes gravity continues to propagate at light speed as space expands, gradually diminishing its ability to pull distant galaxies back together. Some speculative theories propose that dark energy might change over time, potentially reversing the cosmic acceleration in the distant future. These scenarios must carefully account for how quickly gravitational effects propagate to remain consistent with observations confirming that gravity travels at light speed. Another fascinating implication involves gravitational waves from the early universe. Inflation should have produced primordial gravitational waves that, if detected, would provide crucial information about the universe when it was less than a trillionth of a second old. The spectrum of these waves depends on gravity propagating at light speed, providing another test of this fundamental aspect of general relativity. As you rest comfortably under the gentle pull of Earth's gravity, consider that this same force, propagating at precisely the speed of light, shapes the evolution of the entire cosmos. From the smallest scales to the largest, from the earliest moments to the far future, the fact that gravity travels at light speed profoundly influences the universe we observe. The finite speed of gravity ensures that cause and effect remain properly ordered throughout the cosmos, preventing the logical paradoxes that might arise if gravitational information could travel instantaneously. This limitation, far from being restrictive, provides the reliable framework of causality within which the rich tapestry of cosmic evolution unfolds. As we drift towards sleep, we can take comfort in the elegant consistency of our universe. The same physical principles that keep us grounded on Earth also govern the dance of galaxies across billions of light-years of space. Gravity's speed, precisely matched to the speed of light, weaves space, time, and matter into the coherent cosmic whole, of which we are a small but connected part. While experiments have confirmed that gravity propagates at the speed of light with remarkable precision, many questions about gravity's fundamental nature remain unanswered. Scientists around the world continue to probe the mysteries of gravitational physics through increasingly sophisticated experiments and theoretical work. Let's explore the frontiers of this research and the open questions that still intrigue physicists studying gravity's speed. One of the most active areas of investigation concerns the quantum nature of gravity. If gravity is transmitted by particles called gravitons, as most theoretical frameworks suggest, then detecting these particles would provide crucial insights into how gravitational effects propagate. However, individual gravitons would interact so weakly with matter that direct detection poses enormous challenges. Several creative approaches are being explored to overcome these challenges. Some scientists propose looking for the collective effects of many gravitons, such as subtle quantum noise in gravitational wave detectors. Others suggest searching for graviton-related signatures in the cosmic microwave background radiation, or in high-energy particle collisions. The European Space Agency's LISA Laser Interferometer Space Antenna mission, planned for launch in the 2030s, might help in this quest. By detecting gravitational waves from space, free from Earth-based disturbances, LISA could potentially observe quantum effects in gravitational wave propagation that might reveal properties of gravitons. Another fascinating area of research involves testing gravity's behavior at extreme distances. While we know gravity travels at light speed over astronomical distances, some modified gravity theories predict tiny deviations that might become apparent only across intergalactic or even cosmological scales. The Square Kilometre Array, an enormous radio telescope network under construction across Australia and South Africa, will track pulsars with unprecedented precision. This pulsar timing array could detect ultra-low frequency gravitational waves traveling billions of light years, potentially revealing whether gravity behaves exactly as Einstein predicted over these vast distances. At the other extreme, scientists are investigating gravity's behavior at subatomic scales. The interplay between gravity and quantum mechanics remains poorly understood, and some theories suggest that gravity might behave differently at very short distances. Tabletop experiments searching for deviations from Newton's inverse square law at microscopic distances continue to improve in sensitivity. These experiments use tiny torsion balances, or microresonators, to measure gravitational forces between small masses, looking for signs that gravity might strengthen or weaken differently than expected at small scales. Some researchers are developing experiments to test whether gravity indeed transmits quantum entanglement. According to general relativity, the gravitational field of a mass in a quantum superposition should itself be in a superposition. Detecting this gravitationally induced entanglement would confirm that gravity transmits quantum information at light speed, just as it transmits classical information. A team led by physicists Sugata Bose and Mauro Paternostro has proposed an experiment using tiny diamonds in quantum superposition states to test this idea. By placing these diamonds in slightly different locations and allowing them to interact only gravitationally, they hope to detect whether gravity can create quantum entanglement between them. Another open question concerns whether the speed of gravity might vary over time. While current evidence shows it matches the speed of light precisely, some theories suggest that fundamental constants might have evolved throughout cosmic history. Observations of very distant gravitational wave sources might eventually allow scientists to test whether gravity propagated at exactly the same speed billions of years ago as it does today. Researchers are also investigating whether gravity's speed might depend on the environment. Around rapidly rotating black holes, space-time becomes twisted in a process called frame dragging. Some theories suggest that this extreme distortion of space-time might affect how gravitational waves propagate through these regions, potentially causing tiny variations in their effective speed or polarization. The Event Horizon Telescope, which captured the first image of a black hole's shadow in 2019, continues to improve its capabilities. Future observations might detect the effects of frame dragging on light and, indirectly, provide insights into how gravitational effects propagate in these extreme environments. An intriguing area of research involves the relationship between gravity and information. Black holes present a fascinating paradox. According to quantum mechanics, information cannot be destroyed, but objects falling into black holes seem to disappear completely. Physicist Stephen Hawking proposed that black holes slowly evaporate through quantum effects, potentially allowing information to escape, but the precise mechanism remains unclear. This black hole information paradox connects to questions about how quickly gravitational information propagates. Some proposed resolutions involve subtle quantum effects that might modify how gravitational information travels near black hole horizons. The gravitational wave signals from black hole mergers, already detected by LIGO and Virgo, provide valuable data for testing these ideas. As detection sensitivity improves, scientists hope to observe the ring-down phase after a merger in greater detail, potentially revealing quantum effects at the black hole horizon that could shed light on how gravitational information propagates. Another frontier involves testing whether all types of energy gravitate at the same rate and whether gravitational waves of different frequencies travel at exactly the same speed. Einstein's equivalence principle, a cornerstone of general relativity, suggests they should, but some quantum gravity theories predict tiny deviations. Future space-based missions might test these predictions by observing gravitational waves across a wider frequency range than Earth-based detectors can access. The DeCIGO (deci-Hertz interferometer) gravitational wave observatory concept, proposed by Japanese scientists, would operate in a frequency band complementary to LISA and LIGO, potentially allowing more precise tests of whether gravitational waves of different frequencies propagate identically. The relationship between gravity and the other fundamental forces remains one of physics' greatest mysteries. The Standard Model of particle physics successfully describes the electromagnetic, weak, and strong nuclear forces, but it doesn't include gravity. Creating a unified theory that encompasses all four forces has been a dream of physicists since Einstein's time. String theory and loop quantum gravity represent two major approaches to this unification, each with implications for how gravitational effects propagate. Testing these theories requires probing energy scales far beyond what current particle accelerators can achieve. But astronomical observations of extreme events like neutron star mergers provide a natural laboratory for testing predictions about gravity's behavior. An exciting area of research uses gravitational waves to probe the early universe. Primordial gravitational waves generated during cosmic inflation would carry information about physics at energy scales far beyond what particle accelerators can reach. Various experiments, including advanced cosmic microwave background telescopes like the Simons Observatory and CMB-S4, are searching for the imprint these waves would leave on the polarization of the cosmic microwave background radiation. Detecting these primordial gravitational waves would not only confirm the inflation theory, but also provide insights into the quantum nature of gravity. Their spectrum and properties would test predictions of various quantum gravity approaches regarding how gravitational effects propagated in the extreme conditions of the early universe. Some researchers are exploring whether gravity might emerge from more fundamental quantum processes rather than being a primitive force. In these emergent gravity scenarios, what we experience as gravitational attraction arises from the collective behavior of microscopic quantum degrees of freedom, similar to how temperature emerges from the random motion of atoms. Theoretical physicist Erik Verlinde has proposed that gravity might be an entropic force, arising from the tendency of physical systems to increase their entropy. This controversial idea suggests a new perspective on how gravitational effects propagate, potentially connecting the speed of gravity to the fundamental speed at which quantum information can spread. Another frontier involves testing whether gravity obeys the same symmetry principles as the other forces. The Standard Model relies on principles like Lorentz invariance, which ensures that physical laws remain the same regardless of one's velocity. Some quantum gravity approaches suggest tiny violations of these symmetries that might affect how gravitational waves propagate over vast distances. Observations of high-energy cosmic rays and gamma-ray bursts provide constraints on these potential violations. Future gravitational wave observations from sources billions of light-years away would provide even more stringent tests, as tiny effects would accumulate over these enormous distances. The mystery of dark energy, the force driving the accelerating expansion of the universe, may also connect to questions about gravity's propagation. Some modified gravity theories attempt to explain dark energy by changing how gravitational effects propagate over cosmological distances. The 2017 neutron star merger observation severely constrained many of these theories by confirming that gravity travels at light speed, but more subtle modifications remain possible. Upcoming projects like the European Space Agency's Euclid mission and NASA's Nancy Grace Roman Space Telescope will map the universe's large-scale structure with unprecedented precision. These observations will further constrain how gravity behaves on cosmic scales, potentially revealing subtle effects that might connect to the dark energy mystery. As technology advances, scientists continue to develop new methods for studying gravitational physics. Atom interferometers, which use the wave nature of atoms to detect tiny changes in gravitational potential, offer promising new ways to test gravity at quantum scales. These devices might eventually achieve the sensitivity needed to detect gravitational waves in frequency ranges complementary to LIGO and LISA, opening new windows on the gravitational universe. Developments in quantum information science might also provide new tools for studying gravity's quantum nature. Quantum sensors exploiting properties like superposition and entanglement can achieve remarkable sensitivity to tiny forces. Future quantum technologies might allow direct detection of individual gravitons or other subtle quantum aspects of gravity's propagation. The quest to understand gravity's speed connects to some of the deepest questions in physics. How do space and time emerge from quantum reality? What happened at the Big Bang? Is space-time fundamentally continuous or discrete? Are there additional dimensions beyond the 3 spatial and 1 temporal dimension we directly experience? Each of these questions relates to how quickly gravitational effects propagate. The observation that gravity travels at exactly the speed of light provides a crucial constraint on potential answers, guiding researchers toward theories that respect this fundamental aspect of reality while potentially revealing new physics in extreme regimes. As you drift towards sleep, imagine the scientists around the world working to unravel these mysteries, designing ever more precise experiments, developing mathematical frameworks, and scanning the cosmos for subtle clues about gravity's true nature. Their quest continues the journey that began with Newton's apple and Einstein's equations, pushing the boundaries of human knowledge about the fundamental force that shapes our universe. The open questions about gravity's speed and nature remind us that science is a never-ending journey of discovery. Each answer reveals new questions. Each insight opens new mysteries to explore. Perhaps the most beautiful aspect of this ongoing quest is that it connects the largest scales of the cosmos to the smallest quantum fluctuations, weaving together our understanding of reality into an ever more coherent and elegant tapestry. Beyond the mathematics and experiments, the discovery that gravity travels at the speed of light invites profound philosophical reflection. This fundamental aspect of our universe shapes not only the physical cosmos, but also how we understand causality, connection, and our place within the grand tapestry of existence. Let's explore these deeper implications, considering what gravity's finite speed means for our understanding of reality. The finite speed of gravity establishes a fundamental limit on causal influence. Nothing, not even gravitational information, can travel faster than light. This cosmic speed limit ensures that causes always precede their effects, maintaining the arrow of time that gives our universe its orderly progression from past to future. Imagine if gravity propagated instantaneously, as Newton's theory implied. Such instantaneous action at a distance would allow for causal paradoxes, where effects might precede their causes when viewed from different reference frames. The universe would lose the orderly relationship between events that makes reality comprehensible and predictable. Instead, gravity's light speed propagation creates what physicists call a light cone for each event in space-time. This cone separates the regions that can be causally connected to the event from those that cannot. No matter how massive an object, its gravitational influence cannot reach beyond this cone. Even black holes, the most extreme gravitational entities in the universe, are bound by this limitation. This causal structure imposes a profound locality on the universe. Events can only directly influence their immediate surroundings, with these influences gradually propagating outward at light speed. The ripples of causality spread like waves on a pond, binding the cosmos together while maintaining its logical coherence. Consider what this means for our connection to the cosmos. When you gaze at the night sky, you're not seeing stars as they are now, but as they were when their light began its journey to Earth. The star Proxima Centauri appears to us as it was about 4.2 years ago. More distant stars may have died centuries or millennia ago. Their demise still unknown to us because neither light nor gravitational waves from those events have reached Earth yet. This delay in gravitational influence means that if the Sun were to suddenly disappear, Earth would continue orbiting the vacant space for about 8 minutes and 20 seconds before the gravitational change reached us. Only then, simultaneously with the darkness as the last light reached us, would Earth fly off in a straight line, freed from its gravitational tether. This finite propagation speed creates a profound separation between events and our knowledge of them. In a sense, we live in a perpetual temporal bubble, our present moment defined by information that reaches us now, rather than by what exists now across the universe. The concept of universal simultaneity, of a cosmic now, dissolves when we recognize that gravity and light take time to travel. This realization challenges our intuitive understanding of time and space. What we call now is different for observers in different locations, not merely because of subjective experience, but because of the fundamental structure of space-time itself. Einstein's theories reveal that time and space are not absolute but relative, woven together in a four-dimensional fabric whose properties emerge from the finite speed of causal influence, including gravity. The fact that gravity travels at precisely the same speed as light suggests a deeper unity in nature. These seemingly different phenomena, one a force pulling masses together, and the other the propagation of electromagnetic waves, share this fundamental speed. This coincidence hints at an underlying connection between gravity, light, space, and time, pointing toward Einstein's insight that gravity is not a force, but the curvature of space-time itself. This unity invites us to reconsider traditional distinctions between force and structure, between objects and the space they inhabit. In general relativity, masses don't merely exist within space, they shape it. The gravitational attraction we feel toward Earth isn't a force pulling us downward, but the result of Earth's mass curving the space-time around it. We move along the straightest possible path in this curved space-time, which feels to us like being pulled toward the ground. The finite speed of gravity also shapes our cosmic horizons. Because the universe is expanding and this expansion is accelerating, regions beyond a certain distance are receding from us faster than light. No signal, gravitational or electromagnetic, can ever reach us from these regions, placing them permanently beyond our causal influence. This cosmic horizon, determined by the finite speed of causal influence, limits what we can potentially know about the universe. Some regions will forever remain invisible to us, their existence inferred but never directly observed. This humbling constraint reminds us that our perspective is limited, our knowledge incomplete, not merely due to practical limitations, but because of the fundamental structure of reality. Yet within these constraints, the finite speed of gravity creates a universe of remarkable beauty and complexity. The gravitational waves rippling through space-time at light speed carry information about distant cosmic cataclysms, allowing us to hear the universe in a new way. The interplay between gravity's finite speed and the expansion of space shapes the cosmic web of galaxies, creating the rich structure we observe across billions of light-years. The light-speed propagation of gravity also ensures that the universe maintains a delicate balance between stability and change. If gravity traveled much faster or slower than light, cosmic structures might evolve very differently. Stars might burn out more quickly or never form at all. Galaxies might dissolve or collapse. The cosmic dance that eventually led to our existence depends on gravity propagating at precisely this speed. This realization connects to the anthropic principle, the observation that the fundamental properties of our universe appear finely tuned to allow for the emergence of complexity and life. The fact that gravity travels at light speed is one aspect of this apparent tuning. In a universe where gravity propagated at a significantly different speed, the conditions for our existence might never have arisen. Does this suggest purpose or design in the cosmos? Or is it merely that, in a vast multiverse of different possible universes, we necessarily find ourselves in one where the conditions allow for our existence? These questions take us to the frontier where physics meets metaphysics, where scientific models encounter their explanatory limits, and philosophical reflection begins. The finite speed of gravity also shapes our understanding of human knowledge and scientific progress. Newton's theory of instantaneous gravitational action worked remarkably well for centuries, despite being fundamentally incorrect about gravity's speed. This reminds us that scientific theories can be tremendously useful while still being incomplete or even wrong in certain aspects. Einstein's revolution didn't invalidate Newton's practical achievements, but revealed deeper truths about reality that Newton couldn't access. This pattern of scientific progress, where new theories don't merely replace but encompass and transcend older ones, suggests that our current understanding of gravity will likely be similarly transcended. Future theories may reveal that what we now call the speed of gravity emerges from even deeper principles we haven't yet glimpsed. This humility about our current knowledge is balanced by wonder at what we have managed to discover. That humans, evolved on a small planet orbiting an ordinary star, have determined that gravity propagates at precisely the speed of light is a remarkable achievement. Our minds, products of the very cosmos we study, have somehow grasped this fundamental aspect of reality through observation, mathematics, and creative insight. The finite speed of gravity also shapes our existential understanding of connection and isolation in the universe. No matter how distant two objects are, they remain gravitationally connected, though the influence takes time to travel. Every massive object in the cosmos is sending out gravitational messages at this moment, ripples in space-time that will gradually reach across vast distances. Yet this connection comes with a temporal delay that creates a kind of cosmic loneliness. The gravitational waves reaching Earth from distant galaxies tell us about events in the distant past. Our gravitational influence propagates outward at light speed, touching future states of distant cosmic regions we will never directly know. We are connected to the cosmos by these invisible threads of gravitational influence, yet separated by the inexorable delay their finite speed imposes. This tension between connection and separation mirrors our human experience. We reach out to others through communication that takes time to propagate, never quite able to bridge the gap between minds, yet finding meaning in the attempt. The gravitational web binding the cosmos becomes a metaphor for the web of relationships binding human society, each with its limitations and possibilities. The fact that nothing, not even gravity, can exceed the cosmic speed limit brings a certain democratic equality to the universe. No object, regardless of its mass or energy, can exert instantaneous influence across space. Even black holes, with their seemingly absolute gravitational dominance, are bound by this limitation. Their gravitational influence, like that of all objects, propagates outward at exactly light speed. This equality of influence challenges hierarchical views of the cosmos and reminds us of the profound interconnectedness of all things. Each object, from subatomic particles to supermassive black holes, participates in the same gravitational conversation, sending out ripples that travel at the same fundamental speed. As you drift towards sleep, consider how these gravitational waves pass through your body at this very moment, subtle ripples in the fabric of space-time connecting you to distant cosmic events. Feel the gentle pull of Earth's gravity holding you in place, a force propagating at precisely the speed of light from the planet's center to where you rest. Imagine the vast cosmic web of gravitational influence, billions of massive objects sending out their signals at light speed, creating the invisible architecture within which galaxies form, stars burn, and life evolves. This web, constrained by the finite speed of gravity, creates the conditions that make our existence possible. The philosophical implications of gravity's light speed extend into our understanding of freedom and determinism. The cosmic speed limit ensures that causality maintains its directional flow, that effects cannot precede their causes. Yet within this causal framework, quantum indeterminacy introduces an element of fundamental unpredictability. The universe appears neither completely determined nor completely random, but a complex interplay of law and chance. Perhaps this balance between order and possibility, between the constraints imposed by gravity's finite speed and the openness created by quantum uncertainty, provides the perfect conditions for the emergence of complexity and consciousness. In a universe too rigid or too chaotic, minds capable of pondering these questions might never have evolved. As your consciousness gradually fades into sleep, you remain cradled in this intricate gravitational web, part of a cosmos whose fundamental nature includes the beautiful constraint that gravity, like light, takes time to travel across the vastness of space. This limitation, far from diminishing the universe's wonder, enhances it, creating a reality of remarkable richness, complexity, and beauty within which we have the privilege to exist and wonder. As our journey through the mysteries of gravity's speed comes to a close, let us pause to consider the beauty of what we've discovered. The question we began with, does gravity travel faster than light, has led us through centuries of scientific inquiry, from Newton's apple to Einstein's equations, from astronomical observations to cutting-edge gravitational wave detectors. And the answer, confirmed with remarkable precision by the 2017 neutron-star merger, is both simple and profound. Gravity travels at exactly the speed of light. This conclusion, far from being a mere technical detail, reveals something fundamental about the nature of our universe. Gravity, the force that shapes the largest structures in the cosmos and keeps our feet planted firmly on Earth, propagates at precisely the same speed as light, the electromagnetic waves that allow us to see the world around us. This equivalence hints at a deep unity underlying the apparent diversity of natural phenomena. As you drift towards sleep, imagine the gravitational influence of every object in the cosmos spreading outward at light speed, a vast and intricate web of influence binding the universe together across space and time. From the smallest subatomic particles to the largest galaxy clusters, everything that has mass or energy contributes to this gravitational conversation, sending ripples through the fabric of space-time that travel at precisely 299,792,458 meters per second, no faster, no slower. Consider the Sun, whose gravitational embrace holds Earth in its orbit 93 million miles away. The gravitational information from the Sun takes just over 8 minutes to reach us, the same time as its light. If the Sun were to somehow disappear, we would continue orbiting the vacant space for those 8 minutes, unaware of the change until both the gravity and light from the Sun ceased to reach us simultaneously. This finite propagation speed creates a profound temporal structure in our universe. Nothing can influence anything else instantaneously. Every cause must wait for its effects to unfold as information travels at light speed. This limitation, far from being a constraint that diminishes the universe, is a crucial part of what makes reality coherent and comprehensible. Imagine if gravity were instantaneous, as Newton's theory implied. Such action at a distance would create the possibility of causal paradoxes, where effects might precede their causes when viewed from different reference frames. The orderly relationship between events that gives meaning to concepts like before and after might break down. Our universe would lose the logical progression that makes scientific understanding possible. Instead, gravity's light speed propagation ensures that causality remains intact throughout the cosmos. Events unfold in a logical sequence, with causes always preceding their effects. This causal structure provides the stable framework within which the rich complexity of the universe can emerge and evolve. The fact that gravity travels at light speed also tells us something profound about the nature of space and time themselves. In Einstein's general relativity, gravity isn't a force transmitted through space, but a manifestation of space-time curvature. Matter and energy shape the geometry of space-time, creating the curves and dips that we experience as gravitational attraction. When a massive object moves, it creates ripples in this space-time fabric. gravitational waves that propagate outward at exactly light speed. These waves carry information about changes in the gravitational field, allowing distant objects to feel these changes after an appropriate delay. This view of gravity as space-time curvature reveals that the speed of gravity isn't merely the speed of a force or interaction, but reflects something more fundamental: the rate at which changes in the very structure of reality can propagate. The fact that this speed matches the speed of light suggests that space, time, gravity, and light are intimately connected aspects of a unified cosmic framework. The confirmation that gravity travels at light speed represents a triumph of human curiosity and ingenuity. It required developing theories of unprecedented mathematical sophistication, building detectors of extraordinary precision, and observing cosmic events billions of light years away. That we, creatures who evolved on a small planet orbiting an ordinary star, have managed to determine this fundamental aspect of reality is nothing short of remarkable. Yet this achievement is just one milestone in our ongoing quest to understand the cosmos. Many questions about gravity remain unanswered, particularly regarding its behavior at quantum scales and its relationship to the other fundamental forces. The journey of discovery continues, with each answer revealing new mysteries to explore. As you drift towards sleep, imagine the gentle gravitational waves from distant cosmic cataclysms passing through your body at this very moment. Subtle ripples in space-time, traveling at light speed across the vastness of the universe. Too weak to detect without the most sensitive instruments, these waves nevertheless connect you to events in distant galaxies, a reminder of our place within the larger cosmic whole. Feel the steady pull of Earth's gravity, holding you safely in place, an embrace that travels from the planet's center to your resting form at exactly light speed. This same force that keeps the moon in orbit and guides the planets around the sun also keeps you grounded, a participant in the gravitational conversation that binds all matter. Consider the remarkable coincidence that we live in a universe where the speed of gravity is precisely calibrated to allow for the emergence of stable stars, planets, and eventually life. If gravity propagated significantly faster or slower than light, the cosmic evolution that led to our existence might have unfolded very differently. The light speed propagation of gravity creates a delicate balance between order and possibility. Fast enough to bind cosmic structures together, yet finite enough to prevent instantaneous action at a distance, this speed helps create a universe that is neither too rigid nor too chaotic. A universe capable of developing the remarkable complexity we observe around us. The question of gravity's speed connects to some of the deepest puzzles in contemporary physics. The apparent conflicts between general relativity and quantum mechanics, the mysteries of dark energy and dark matter, the quest for a unified theory of fundamental forces. All these frontiers of research touch on how gravitational effects propagate through space-time. While the evidence confirms that gravity travels at light speed under normal conditions, theoretical explorations continue to probe whether tiny deviations might occur in extreme environments or at quantum scales. These investigations may eventually lead to new discoveries that deepen our understanding, just as Einstein's work built upon and transcended Newton's. As our scientific journey continues, the philosophical implications of gravity's finite speed invite reflection. This fundamental constraint shapes not only the physical universe, but also how we understand our place within it. The light speed propagation of gravity reminds us that we are both connected to and separated from the cosmos, connected through the gravitational web that binds all matter, yet separated by the time it takes for these influences to travel across space. This tension between connection and separation mirrors our human experience. We reach out to others, yet perfect communication remains impossible. We are part of a larger whole, yet maintain our distinct identities. The universe's structure, with its light speed limitation on gravitational propagation, perhaps reflects something essential about the nature of existence itself, both unified and diverse. both determined and open to possibility. The fact that nothing, not even gravity, can exceed the cosmic speed limit brings a certain egalitarianism to the universe. No object, regardless of its mass or energy, can exert instantaneous influence. Even black holes must wait for their gravitational effects to propagate at light speed. This limitation ensures that no single entity can dominate the cosmos completely, creating space for the diverse tapestry of cosmic structures we observe. Think of the night sky above you now, filled with stars whose light and gravitational influence reach us after journeys of many years. The star Proxima Centauri, our nearest stellar neighbor, appears to us as it was about 4 years ago, its gravitational pull reaching us after the same journey time. More distant stars, galaxies, and quasars send their gravitational signatures across vast cosmic distances, all traveling precisely at light speed through the intervening spacetime. This steady procession of gravitational influence, moving outward from every massive object at exactly light speed, creates a cosmic symphony of interaction. Galaxies orbit within clusters, stars orbit within galaxies, planets orbit stars, moons orbit planets, all guided by gravitational information propagating at the cosmic speed limit. Consider the remarkable precision with which we've confirmed gravity's speed. The detection of gravitational waves from the neutron star merger GW 170817, followed just 1.7 seconds later by gamma rays from the same event, allowed scientists to determine that gravity travels at light speed to within 1 part in 10 to the power of 15. Such extraordinary precision testifies to both the remarkable accuracy of Einstein's theory and the incredible achievements of observational astronomy. The speed of gravity's propagation also shapes our understanding of cosmic history. When we observe distant galaxies, we see them as they were billions of years ago, their light having taken billions of years to reach us. Similarly, their gravitational effects arrive after exactly the same journey time. This means that the cosmic structures we observe are shaped by gravitational interactions that began in the distant past, propagating through space-time at light speed to create the universe we see today. The expansion of the universe itself interacts with gravity's finite speed in fascinating ways. As space expands, it stretches the wavelengths of light, creating the redshift astronomers observe in distant galaxies. Similarly, it stretches gravitational waves, lowering their frequency as they travel across expanding space. Both phenomena respect the same cosmic speed limit, their journeys shaped by the same fundamental principles. In regions where space expands so rapidly that objects recede from us faster than light, we encounter a profound limit. No signals, whether light or gravitational, can ever reach us from beyond this cosmic horizon. This boundary, determined by the finite speed of causal influence, marks the edge of our observable universe. Beyond it lie regions forever invisible to us, their existence inferred but never directly detected. As your body grows heavier with approaching sleep, feel how Earth's gravity holds you safely in place. This gravitational attraction propagates from the planet's core at light speed, reaching up to cradle you with precise consistency. The mountains, oceans, atmosphere, and even the people around you contribute their tiny gravitational influences, all traveling at exactly light speed to create the total gravitational field you experience. Think of how gravity's speed helped make your existence possible. The formation of the sun and earth, the chemical processes that allowed life to emerge, the evolution of complex organisms, including humans. All these developments unfolded within the constraints imposed by gravity propagating at light speed. A universe with significantly different gravitational dynamics might never have developed the stable conditions needed for life to evolve. The discovery that gravity travels at exactly light speed also reveals something about the unity of nature's fundamental forces. Of the 4 known fundamental interactions, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, both gravity and electromagnetism propagate at exactly the same speed. This equivalence suggests a deep connection between these apparently distinct aspects of reality, perhaps pointing toward the unified theory that physicists have sought for generations. As you drift closer to sleep, imagine the vast cosmic web of galaxies and dark matter that spans the observable universe. This intricate structure, shaped by gravity acting over billions of years, could only form as it has because gravity propagates at light speed. The delicate balance between the universe's expansion and gravity's binding influence depends critically on this fundamental speed limit. Consider also how the fact that gravity travels at light speed ensures the coherence of cosmic evolution. If gravitational effects propagated instantaneously, the universe might evolve too quickly or chaotically for stable structures to form. If gravity traveled much slower than light, cosmic structures might never bind together effectively. Instead, we live in a universe where gravity propagates at exactly the right speed to allow for the rich cosmic tapestry we observe. The confirmation that gravity travels at light speed represents not just a scientific fact, but a profound insight into the orderly nature of reality. In a universe governed by comprehensible laws, where effects follow causes in predictable ways, we find both meaning and beauty. The cosmic speed limit, rather than constraining possibility, creates the conditions for an astonishingly rich and diverse universe. As your consciousness begins to fade, imagine once more the invisible gravitational waves passing through your body at this moment. From distant black hole mergers, neutron star collisions, and other cosmic cataclysms, these ripples in space-time travel at light speed across billions of light years before washing through Earth. Too weak to feel without special instruments, they nevertheless connect you to the most energetic events in the cosmos. The steady rhythm of your breathing matches the steady propagation of gravity at light speed throughout the universe. Each breath, each heartbeat, occurs within a framework of space-time, shaped by gravitational influences that travel at precisely the cosmic speed limit. Your very existence is cradled within this fundamental aspect of reality. As your consciousness gently fades into sleep, you remain held in Earth's gravitational embrace, a force transmitted at light speed through the invisible threads of warped space-time. You are cradled in this fundamental aspect of reality, as are the moons, planets, stars, and galaxies throughout the cosmos. Gravity's reach extends throughout the universe at precisely light speed, binding matter into planets, stars, and galaxies, while maintaining the orderly progression of cause and effect that gives the cosmos its comprehensible structure. This gentle constraint, far from limiting the universe's potential, creates the conditions for its remarkable beauty and complexity. In the mystery of gravity's speed, we glimpse something profound about the nature of reality, its unity amid diversity, its balance between constraint and possibility, its capacity to generate complexity from simple principles. The fact that gravity travels at exactly the speed of light reflects a deep harmony in the cosmos, a precise calibration that helps make our existence possible. So rest now, embraced by gravity's gentle reach, connected through invisible waves of space-time curvature to the vast cosmic whole. As you sleep, the gravitational influence of countless celestial bodies continues to wash over you at light speed, a reminder that even in the quietest moments, you remain a participant in the grand cosmic conversation, bound by the same fundamental principles that govern the largest scales of the universe. The speed of gravity, precisely matched to the speed of light, creates the stable yet dynamic reality within which we live and dream. Neither faster nor slower than light, gravity propagates at exactly the right speed to create a universe capable of wondering about its own fundamental nature. In your final moments of wakefulness, imagine once more that web of gravitational influence extending throughout the cosmos at light speed, binding matter into the structures that make up our universe. From the gentle tug that keeps your body on Earth, to the massive forces shaping galaxy clusters billions of light years away, this invisible network, propagating at precisely light speed, creates the stage upon which the cosmic drama unfolds. And as you finally surrender to sleep, know that you do so within this gravitational embrace, held safely by forces that travel throughout the universe at exactly the speed of light, no faster, no slower, exactly as they should be. The universe continues its dance, gravity propagating at light speed through the vast cosmic darkness, as your consciousness drifts into the peaceful realm of dreams. Sleep now, wrapped in the unseen pull of gravity, which travels at light speed across the cosmos, binding the universe together with its gentle, unwavering reach.